Hello everyone. Today we are going to present support vector mission from group 8. These are the contents we are going to discuss today. This is Ramya. Now I am going to explain what is meant by support vector mission. Support vector mission is supervised learning model that uses an algorithm to find a hyperplane in an n-dimensional space that can distinctly classify the data points. The other concepts in SVM model are support vectors. Support vectors are data points that are closer to the hyperplane, which influence the position and orientation of the hyperplane. Using these support vectors, we maximize the margin of the classifier. Deleting the support vectors will change the position of the hyperplane. These are the points that help us build our SVM better. There are many possible hyperplanes. What is best possible hyperplane? To separate the two classes of data points, there are many possible hyperplanes that could be chosen. Our objective is to find a plane that has the maximum margin, that is, the maximum distance between data points of both classes. Maximizing the margin distance provides some reinforcement so that future data points can be classified with more confidence. Let's move on to the hyperplane in n-dimensional space. Hyperplanes are decision boundaries that helps to classify the data points. Data points falling on either side of the hyperplane can be attributed to different classes. Also, the dimension of the hyperplane depends on the number of features. If the number of input features is 2, then the hyperplane is just a line. Whereas, if the number of features is 3, then the hyperplane becomes a two-dimensional plane. Let's a question for classmates. What is meant by margin in SVM? Margin is the distance of closest tuples or points from the decision line or hyperplane.
Hi everyone. Um, I'll be talking about linear SVM. Linear support vector machine classifies data into two classes. In linear SVM, the hyperplane has the largest margin around the decision boundary that separates the data. So in two-dimensional space, it is a line, and three-dimensional space, it's a plane. The decision boundary or the hyperplane can be written in the form of w dot x plus b equal to 0, where x is a document or a data and w comma b are boundary variables. The hyperplane divides the document into planes. One is negative and a positive, which can be classified using the equation given in the slide. So if x1 and x2 are considered as 2 points, then the margin or the distance can be calculated by the equation 2 divided by w. So the data is called linearly separable if it can be separated perfectly by linear SVM hyperplane, which is difficult if many noise documents exist. And the question for the class: in how many classes does linear SVM classifies the data, and what is the shape in 2D space? The answer is linear SVM classifies data in two classes, and hyperplane in 2D space is a line.
Hello everyone. Today we are going to discuss about learning a linear SVM model. The linear SVM model consists of the two parameters for the decision boundary. Those are W and B. The training phase of the SVM involves in estimating these parameters W and B. These parameters must be chosen in such a way that two conditions are to be met. If y of I is equal to 1, then w into dot product of individual element of xi plus b must be greater than or equal to 1. If y of I is equal to minus 1, then w into dot product of individual element of x plus b should be less than or equal to minus 1. So these conditions should be met for the training phase. These conditions impose the requirements that all training instances from the class 1 and minus 1, that is the squares and the circles, The square should be located above the hyperplane or on the hyperplane, while the instances from the -1 class, that is the circles, must be located on or below the hyperplane. Along with these conditions, SVM also imposes an additional requirement for the margin of its decision boundary, so that it should be maximal. For maximizing this margin, we need to minimize our objective function f of w. This f of w is calculated in such a way that it is the vector product of w into the vector product of w divided by 2. That is, f of w is equal to square of vector product of w by 2. So this is about the linear SVM model. Thank you.
Hello, my name is Akash and I'm part of Group 8. Today I'm going to give you an example of linear SVMs. So assume our dataset has two classes, class A and class B. The class A is represented on this figure 1. The points 3, 1, 3, -1, 6, 1, and 6, -1 are represented with the blue dots, and the class B are represented with the red dots. Just by visual inspection, we can see that the data set is very linear, so we can draw a linear hyperplane which can classify both these classes. So for that purpose, we choose the three support vectors around this hyperplane, represented by the yellow data points, and those are 1, 0, 3, 1, and 3, -1. So from these three support vectors, we get three equations, which are shown in this figure. The -1 and the +1s are the distances from the hyperplane. The -1 represents that we have one point which is on the negative hyperplane and 2 points on the positive hyperplane. Since our SVM is a linear type, we assume that the higher dimensional features represented by phi are an identity function. So we simplify that as 1. And that equations are reduced to these three equations shown in this figure here. And then we substitute the S1, S2, and S3 support vector points into these three equations and solve for alpha 1, alpha 2, and alpha 3. Upon simplification, we get the values to be shown here. And finally, we can get the hyperplane, which can classify the datasets using the line equations, which is shown by y is equal to wx plus b, where w represents the weight of each support vector, x represents the data points, and b represents the bias. So for the weights, we can simply write the equation as the summation of all the alpha parameters and the support vectors themselves, which is given by 1, 0 for the first support vector, 3, 1 for the second, 3, -1 for the third. The 1 here represents the bias, which is equal to 1. And from the above equations, we solve that alpha 1, alpha 2, and alpha 3 are -3.5, 0.75, and 0.75. Upon simplification, we get the points shown here. And from that, we can see that the weights are 1, 0, and biases are -2. From this, we can clearly see that the hyperplane is at 1, 0, and the bias represents -2. With this, the example for linear SVM is complete.
Hello, I'm Sridivya Kirti. Now I'm going to talk about linear SVM non-separable case. In the linearly separable case, SVM tries to find the hyperplane that maximizes the margin with the condition that both classes are classified correctly. But in reality, datasets are probably never linearly separable, so the condition of 100% correctly classified by a hyperplane will never be met. SVM addresses non-linearly separable cases by introducing two concepts, soft margin and kernel tricks. In soft margin, SVM tries to find a line to classify but tolerate one or few misclassifications. In kernel trick, SVM tries to find a non-linear decision boundary. So let's look into the soft margin first. Two types of misclassifications are tolerated by SVM under soft margin. If we look into the figure, in the left one, the dot is on the wrong side of the decision boundary, but on the correct side of the margin. In the right figure, the dot is on the wrong side of the decision boundary and on the wrong side of the margin. Applying soft margin, SVM tolerates a few dots to get misclassified and tries to balance the trade-off between finding a line that maximizes the margin and minimizes the misclassification. Talking about degree of tolerance, how much tolerance we want to give when finding the decision boundary is an important hyperparameter for the SVM. In scikit-learn, it is represented as the penalty term C. The bigger the C, the more penalty SVM gets when it makes misclassification. Therefore, the narrower the margin, the fewer support vectors the decision boundary will depend upon. And now coming to kernel trick. What kernel trick does is it utilizes existing features, applies some transformations, and creates new features. Those new features are the key for SVM to find the nonlinear decision boundary. There are two types of kernel tricks: polynomial kernel, radial basis function kernel. Similar to the penalty term C in the soft margin, gamma is a hyperparameter that we can tune for when we use SVM with kernel. So to sum up, SVM in the linear separable cases, by combining the soft margin and kernel trick together, support vector machine is able to structure the decision boundary for linear separable cases. Hyperparameters like C or gamma control how wiggling the SVM decision boundary could be. The higher the C, the more penalty SVM was given when it misclassifies, and therefore the less wiggling the decision boundary will be. The higher the gamma, the more influence the future data points will have on the decision boundary. Thereby, the more wiggling the decision boundary will be. And the question is, how many types of kernel tricks are there? And what are they? The answer is, there are two types of kernel tricks: polynomial kernel, radial basis function kernel. Thank you.